Next question, number 4 is, it is important question. Let G equal 1 minus 1 I n minus I, and the operation be of multiplication asterisk, and so that G asterisk forms a group. This is the question. Now let's move to the solution part. To show Z comma asterisk forms a group, let's make a composite table, that is Cayley's table first. Yeah, firstly, how many elements are there? 4 elements, so we need 5 cross 5 table we need. So simply we can make 5 cross 5 table. Yes, we can make 1 2 3 4 and 5. Then asterisk is the operation, and elements are 1 minus 1 I minus I, and 1 minus 1 I and minus I, and the product 1 times 1 is 1, 1 times minus 1 is minus 1, 1 times I is I, 1 times minus I is minus I, minus 1 times 1 is minus 1, minus 1 times minus 1 is plus 1, minus 1 times I is minus I, and minus 1 times minus I is plus I. And next step, I1 the I minus 1 is I minus 1 is I minus 1 is minus I, I the. Now the question is, we know I is root under minus 1, squaring on both sides, I square is minus 1, I square is minus 1, and I and minus I, that is I times minus I equal minus I square equal minus 1 equal to 1. So we have to remember this, note down this. So I is I square, that is minus 1, that is minus 1, I minus 1, I times minus I is 1, as I have shown here. And moving to the last, minus I and 1 is minus I, and minus I and minus 1, minus plus I, minus I and plus y is 1, here I have shown, and minus I is plus I square, that is minus 1, this is minus 1. In this way we can form a Cayley's table first. Now we have to show G asterisk forms a group, so we have to go through the properties of this. Now for first closure property or closure axiom, first we have to go through closure axiom. Now for all a comma b belongs to G, a times b, a asterisk b belongs to G. That means, that is, suppose 1 comma minus 1 belongs to G, then 1 asterisk minus 1 equal minus 1 belongs to G. And from this table also, all the elements, the product of all any two elements, that means from the table itself, the product of any two elements is the elements of the given set. From the table itself, it is clear that the product of any two elements, is in the given set, that's why hence G is closed under multiplication operation asterisk. And now move to the second property, that is associative or associate axiom. Second one is, and for this also, for all a b c belongs to G, a asterisk b asterisk c equal a asterisk b asterisk c belongs to G. We may verify this, that means 1 minus 1 and I belongs to G, then 1 asterisk minus 1 asterisk I equal that is 1 asterisk minus I equal minus I, that belongs to G, and 1 asterisk minus 1 asterisk I equal minus 1 asterisk I equal minus I, that also belongs to G, Therefore 1 asterisk minus 1 asterisk I equal 1 asterisk minus 1 asterisk I. So it is it can be satisfied for all the elements of this given set. So, or simply you can write it is true for all the elements of given set. Hence G is associative under the operation asterisk. If we multiply any two, we'll get that result, and again all are in the same table, you can see. That's why associative property or axiom is also verified. Now moving to the third properties, we used 1 2, now 3. 3, that is identity axiom. For identity axiom, we have to suppose let E be the identity element, then 1 asterisk E equal to 1, then simply this implies 1 belongs to Z, minus 1 asterisk E equal to minus 1, that implies E equal to 1 belongs to Z. I asterisk E equal to I, that implies E equal to 1 belongs to Z, and minus I asterisk E equal minus I, that's why E belongs to 1, E equal to 1 belongs to Z. Hence in all case we find E equal to the identity element is 1, hence existence of an identity element is satisfied. So identity axiom, that existence of identity element E equal to 1 is verified as satisfied. Third condition also we have verified. Now let's move to the fourth condition, inverse axiom. For inverse axiom, we have to suppose an inverse element. Let A be the inverse element. Then A asterisk 1 equal to E. That implies A asterisk 1 equal, the value of E is 1. Therefore, or this implies A equal to 1 belongs to Z, and A asterisk minus 1 equal to E, that is A asterisk minus 1 equal to 1. This implies A equal to minus 1, which also belongs to Z. Similarly, A asterisk I equal to E, that is A asterisk I equal to 1. This implies A equal, very interesting, 1 by I. Now interesting point is this, equal 1 is what? Minus 1 by I. We have to do this, and minus 1 is I square by I. This cancel, we obtain minus I, which also belongs to Z. And finally A asterisk minus I equal to E, that implies A asterisk I equal to 1 minus I equal to 1 equal A equal 1 by minus I, that is minus 1 by minus I equal minus cot, minus 1 is I square by I equal to I belongs to G. Be clear that 1 is minus 1 minus 1 is I square, here minus, this cancel and we obtain this, And from all these examples, what we obtain? Hence, the existence of an inverse element is satisfied. Element, existence of inverse. In all, we get the inverse element which is belongs to the given set. That's existence of inverse element is satisfied. All the axioms are satisfied. Therefore, G, asterisk forms a group. In this way, we can prove that, we can show that G equal 1 minus 1 I n minus I forms a group. The next question, question number 5 in our series. It is a binary operation, asterisk defined on the set S equal A comma B comma C is represented in the following Cayley's table. That is given in the same question. A, B, C, A, B and C. The table is also given, and A, B, C, B, C, A and C, A, B, and the instruction is show that S comma asterisk forms a group. Now we have to go through the solution. We have to move to the solution. Here S equal A comma B comma C, and for the first, that is closure axiom, we have to verify closure axiom. It is clear that because the product of any two elements is A, B, C, A, B, C, A, B, C, we obtain A, B, C itself. That's why from the given table, the product of any two elements is also in the same also in the given set. Yes. So asterisk is closed because the product itself ABC or the product of any two elements is in the given set. That's why closure properties is verified. Now second is associative axiom. Yeah, from the given table, you can see from the given table A asterisk B asterisk C equal A asterisk B asterisk C or not, we have to verify. Let's see. Let's see from the table. A asterisk, what is B asterisk C? You can see in the table. Hmm. B asterisk C, B asterisk C, B asterisk uh, C. We can see B asterisk C is A, and here what is A asterisk B? A asterisk B is B. What is A asterisk A? A asterisk A is A. B asterisk C, B asterisk C is also A. It is verified. It is verified. And similarly other relation, since an A belongs to, yes, yeah, other relation can be verified is A asterisk C asterisk C equal to B equal A asterisk C also, and B asterisk B asterisk C equal B equal B asterisk B asterisk C, and so on. Any three relation you can verify those. Hence asterisk is associative. Second part is also verified. Now third property, that is identity property, identity axiom. We have to suppose we have to check here in the table. A asterisk A is A asterisk B is B, and A asterisk C is also C. So here we can check once in the table. A asterisk A is A asterisk B is B, A asterisk C is C. Then what we have learned, that is, we can conclude hence A is an identity element for the operation asterisk. Yes, A asterisk B, and that we discuss A asterisk E equal E asterisk A equal to A. This is the condition of identity axiom. That's why we obtain A asterisk B, A asterisk C is ABC. The same elements we obtain. That's why A is the identity elements. That third condition also verified. Now moving to fourth condition. That is hence an identity element for the operation. Here is the identity element. Existence of identity element is verified. Existence of identity is satisfied. Now fourth number is about inverse axiom. For inverse axiom, yeah, A asterisk A is A asterisk A is A. That implies A inverse equal to A. C asterisk B equal to B asterisk C. That implies B inverse equal to C. and C inverse equal to B. And from the table we can check A asterisk A is A. If A asterisk A is A, the A inverse is A. A inverse is A. C asterisk B is B asterisk C, that B inverse is C and C inverse is B. This shows that each element in yes has an inverse. Now all the axioms are satisfied, therefore yes asterisk forms a group. Yes asterisk forms a group. Now the next question number 6, it is BIMP question, conceptually as well as problem based. Let G equal 0, 1, 2, 3 so that G forms a group. Under the addition modulo, under the addition modulo 4, I have added another part, but not forms a group under the multiplication modulo, under the multiplication modulo 4. This is our question. This is long. I have included both the problem in the same question because comparatively it will be better to understand. That's why here G equal 1 2 oh sorry 0 1 2 and 3. The elements are 4 elements are here. Now Cayley's table for G under the addition modulo 4 is, let's present that here, plus 4 0 1 2 and 3. Here also 0 1 2 and 3. We can close all this. Now 0 plus 0 0 1 2 3 1 0 1 1 1 the 1 1 plus 1 is 2 and 3 1 plus 3 is 4, therefore 4 is 0, remainder will be 0 divided by 4. 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 4 is 0, 2 plus 3 is 5, 5 is 1, 3 plus 0 is 3, 3, 3 plus 0 is 3, 3 plus 1 is 4, 4 is 0, 3 plus 2 is 5, 5 is 1, 3 plus 3 is 6, 6 is 2. Firstly, we have to arrange the table in this way. Now, we have to verify the 4 properties. We have to verify. First, closure axiom. Yeah. After making this table, we can write from the Cayley's table. We see that the product of any two elements of G under the addition modulo 4 is also in G. Hence, plus 4 satisfies the closure axiom. Sometimes you may have confusion how products are. That is, if AB belongs to G, then A asterisk B belongs to G. This is plus 4 addition modulo 4. You can write the operation. If you have confusion, you can write. We can see the operation of any two elements of G under the addition modulo 4. You can manage this. Otherwise, it is okay. Now, moving to the second property, that is, second is associative axiom. Associative axiom. We can take any three elements, since 1 plus 2 plus 3 equal 2 plus 3 is 5, 5 is 1, 1 plus 1 equal to 2, belongs to Z, and 1 plus 2 plus 3 equal 3 plus 3 equals to 2, that is 2, that also belongs to G. Therefore 1 plus 2 plus 3 equal 1 plus 2 plus 3, one result we have shown. uh, Now and the result is true for all the elements of Z under the addition modulo 4. Okay, if instead of that 1 plus 2 plus 3, if you have taken other elements also 0 1 2, you will get the same result. It means therefore plus 4 satisfies the associative axiom, a property that sorry. Now next move to the part that is identity axiom. In this case from the second row and second column of the table, it is clear that 0 is the identity element under the addition modulo 4. Edge 1 plus 0 equal 1, 2 plus 0 equal 2, 3 plus 0 equal 3, 0 plus 0 equal 0. Hence, existence of identity element is satisfied. Now the last is fourth number is inverse axiom. From the table it is clear that 3 plus 1 equal 0. 1 plus 3 equal 0. 2 plus 2 equal 0. Yeah. So the inverse of the inverse of 2 is 2 itself. 3 is 1 and 1 is 3. Similarly, you can check once more. Here you can see in the table. Yes. 3 plus 1 is 0. 1 plus 3 is 0. 2 plus 2 is 0. If you need 0 plus 0 is 0. Yeah. So that is also the elements. Okay. And 0 plus 0 is 0. That is uh, inverse of 2 is 2 itself. 3 is 1. 1 is 3 and 0 is 3. 0 is 0. Therefore, existence of inverse element is satisfied. All the four axioms are fulfilled. Therefore, g comma plus 4 under the addition module 4 is a group. This is the condition. We can verify in this way. We can prove in this. Okay, now let's move to the second part. Second part that we need to verify that under the multiplication modulo 4 is not a group in the same elements. Okay, now Cayley's table for G under multiplication modulo 4 that's simply denoted by cross 4 is presented below. That is cross 4, that's you can see elements are 0, 1, 2 and 3. Oh, very danger table being. Okay, anyway, 0, 1, 2 and 3. You can see 0 times 0 is 0, 0 1 0, all 0. 1 0 is 0, 1 1 is 1, 1 2 is 2, 1 3 is 3, 2 0 is 0, 2 1 is 2 1 is 2, 2 2 is 4, 4 is 0, 2 3 is 6, 6 is 2, 3 0 is 0, 3 1 is 3, 3 2 is 6 is 2, and 3 3 is 9 is 4, 2 is 8 plus 1 is 9. This is the table. Now for closure axiom, first part is for closure axiom. Let's check closure axiom from the table. We see that the product, that is the operation, times 4, yeah, that is the operation, product of any two elements of Z under the multiplication modulo 4. Under the multiplication modulo 4 is also in G, hence satisfied, and multiplication modulo 4 satisfy the closure axiom. closure axiom. First part is this. And moving to number 2, second part, that is associative axiom. Associative axiom. Since 1 times 2 times 3 equal 2 3s are 6, 6 is 2, 1 times 2 equal to 2 belongs to G. 1 times 2 times 3 equal 1 times 2 is 2 times 3, 3 is 6, that is 2 belongs to G. Therefore 1 times 2 times 3 under the multiplication model 4 equal 1 times 2 times 3. The result is true for, yeah, from this the result is true for every element of G. Therefore, for satisfied associative axiom. Now moving to third number, that is identity axiom. Identity axiom.